much the person who came up with CoAP, or worked really hard on it, Hsieh, and he, I've run across work of his over the years in many, many settings, but he's been sort of one of the, I would say, leading industry people behind IoT protocols, and CoAP was sort of one of his pet projects, but before that he'd worked on Zigbee routing. A lot of Zigbee routing was also due to Zach's work, so somebody I have a lot of respect for. You'll notice the slides say ARM. He works, I guess, or did at the point when he was giving this tutorial for that company. And definitely manufacturers of embedded processors like ARM are very much interested in the IoT space. So let's dig right into slide 4, which talks about the Web of Things protocol. And just sort of gives you a very quick high-level overview of it. Basically, it's an IETF standard that runs on top of UDP and has support also for apparently SMS, and gives you some security on top of that. The slide 5 kind of points at why you need a new way to think about client-server mechanisms for this new space. So if you look at a typical sort of web application, the amount of information that's embedded in the packets that are going over the network is on the order of thousands of bytes. So you have to have the IP information, the TLS information, the HTTP information, plus whatever you're requesting, the object's URL information, all of that. If you really add up the number of bytes that you need to describe all of this, it's on the order of thousands of bytes. And as we've discussed over and over again, communication energy is a big part of these devices. The reason the radio duty cycling work exists, that we talked about last time, is because keeping the radio on, sending information over the radio is really expensive. So cutting down the amount of information you're sending over the radio is really important in that space. In fact, there was a quote from many years ago that every byte a mode transmits brings it a moment closer to its death. So if it's running on AA batteries, literally every byte is part of how long that thing's going to last, right? So you really care about optimizing. So really, if you look at the other end of it, at the individual node, they're running 6-LoWPAN, UDP, the CoAP is sitting on top of that, and the web object. All of this, somehow they managed to compress down to tens of bytes. In fact, what's really, really neat about CoAP is you're turning these little modes into web servers, effectively. So the fact that it's even possible, I thought was pretty amazing, and this protocol aims to achieve that and does. So let's keep going through. A lot of other standards described here, talking about architecture. Typically how things are named on the web, this notion of universal resource identifiers and URLs, and how those things are resolved down to the IP address and port. So actually this set of slides is good because it also kind of reviews what you might know from previous classes. So if you kind of look at how HTTP works, you have a client, you have a server. First you do a TCP three-way handshake, you set up the session. Once you set up the session, you can start from the HTTP. You would send to the server a GET command, which would be acknowledged, and then you would get whatever information you need from the server, and then finally you would tear down that connection. So there's a lot of messaging that happens just to collect a piece of information. There are broadly 2 kinds of paradigms that are used for web applications. I won't get very deep into the differences, but there's something called the REST architecture, and then there's sort of this SOAP services. Roughly speaking, you can think of in the SOAP even how the information is being processed. It's somewhat more general, but it's sort of very heavyweight. Whereas with REST resources, it's just this information sits at the server and is communicated using some standard format, and it's typically very lightweight type of processing that's involved. So here's the REST request, and the next slide is an example. You do a GET, and then you get back the response. CoAP basically tries to emulate this, but then tries to meet a lot of new requirements for the low power systems, having to do with all of these different issues which are described in the design requirements, but I'm going to skip that for now. As we see the details, it'll become a little bit clearer. So the idea of the co-op architecture is that it could coexist with traditional internet-based things. So you could still go to a regular server and make a request for some resource. That server will communicate via HTTP to some proxy, and that proxy will convert HTTP request to CoAP, and then you can send the information that way. So that's sort of part of the CoAP architecture, is that you can make things work easily with what HTTP does. So the point is, it's easy to translate between these two. Let's skip past a little bit. Let's go to slide 18, which talks about the features that CoAP has. So just like you do HTTP : / and the name of a website for your URL, here you do CoAP : / and the name of the URL. So as far as the application is concerned, this is how you access resources over the CoAP protocol. It has an asynchronous transaction model. It uses UDP, so you don't have this notion of a session that's set up and torn down. It's really sort of best effort and connectionless. It has 4 methods. It's very simplified. It has get, it has post, it has put, and it has delete. So you can get resources, you can post some information to the server, you can put things there, you can delete things from the server. It supports URIs. It has a very simple header, just 4 bytes. So it's dramatically simplified. Various other security options exist. We might talk about the block transfer briefly as well. So let's keep moving forward. Slide 20 kind of shows you what that header of a CoAP message looks like. The point that it's being mostly that it's a very small header and essentially has information about message ID is probably really almost the large part of it, and whatever payloads you have. And let's get past a lot of the mundane details here. So let's look at some simple examples like they have on slide 23. So you have a CoAP client that sends an information and has this message ID that goes into the header and asks for the light information, and the server acts back with the same message ID, so you know it's in response to that particular request, and gives you the information about whatever light information it has. It could happen that because it's over UDP, that your request times out. So you make a request to the server, it just doesn't go through, right? Because it's a lossy network, because it's UDP on top of that lossy network, this actually happens more often than you imagine. Packet losses are pretty common. So in that case, the client just waits for a period of time and resends that request, and when the server gets the request, it responds. So that's sort of, as you might imagine. It allows for the possibility of separating the response from the acknowledgement, because our devices might have a sleep cycle associated with them. The request may be asking for information the sensor doesn't even have. So it may be that you're asking for some information that depends on some measurement that is completely event-driven, and that event hasn't occurred. So you're looking for, is there, I don't know, it's a good example of that. Get the temperature of the room when the light is turned off, but maybe right now the light is turned on, right? So whatever URL you're asking for is supposed to connect to that information, but it's not ready yet, the answer that you want. So it might acknowledge that I got the message, I have it stored locally, when the information is available, I will send you back the information. So this is the separate response type of example. A different example might be that I'm about to shut down to go to sleep, I'll respond to you later, this is just to let you know that I got your request. Okay, so it allows for this asynchronous response. That's something that HTTP actually doesn't do. Right? If you ask a web server for information, if it doesn't have it now, you just get an error back, and you should try manually later, but it's not going to take care of getting back to you. It's kind of a weird thing for a website to do, actually. 2 hours later, you're told, here's the page, right? But when you're talking machine to machine, that actually makes sense, because at the other end is not a human waiting for 2 hours, it knows to wait for it. The next slide 26 actually gets into some of the nitty-gritty details, like where is the get information in the header, where's the content in the header, where's the message ID stored, and all of that, so you can kind of see the details of it. But it's a very simple protocol, and it really doesn't get more simpler. Here's an example of proxying on slide 28. So you have an example where the client is HTTP and the server is a CoAP server. I don't know that the example you're working with for your project is like this, but you can very easily set up a there are CoAP clients for like the Chrome browser or Fox extensions that you're going to connect to the CoAP URL from the laptop and from a browser that's an HTTP browser, if you will, and it will communicate to a proxy, and that proxy will translate. Or I think in the case of some of these extensions, they're even acting as a proxy locally. So you might have a request coming that's an HTTP GET request. The proxy converts that to a CoAP GET request. The CoAP server responds, and then continue the way you do it. The information in case of a proxy could even be cached, so that further requests that come in for the exact same URL are just responded from the cache, depending on what cache policies the proxy server is implementing. This is a very standard web stuff. There's something called observe, which is a kind of GET request that allows you to get multiple responses as something might change. So over time, there's this notion of what they call here a token, where you make the request, and you can see there's sort of a multiple times when the same information is being sent back from the server, and maybe this request had to do with notify me whenever the light changes. Right? And so every time the light changes, you send back a message. So it allows for much more persistent communication than is typical with HTTP. That's one way to see the difference between HTTP and CoAP. There's something called block transfer. So because the packets are kind of small, and you might be asking for a lot of information that doesn't quite fit in, or the information you're asking for is really long. So there's also this notion of you ask for the information, and it sends you responses one after the other in this case. So first it acts back with one of the blocks, and then you ask for some additional information, and it responds to that. You ask for more information, it responds to that sort of. So it's actually back and forth. It's not just all streaming down from the server, but you're asking for more information as you get it. So the next slide just talks about different CoAP resources. There is a library for any programming environment you're used to, like C or Java, where you can just code stuff up so that you can directly use that as a client to communicate with, or there's even servers that are designed. And many commercial products already have kind of CoAP built into them. And Contiki in particular has CoAP support, as mentioned here, which is what your project is about. So the homework assignment in the CoAP, is it just two nodes talking directly to each other? What was those? But it's with the real devices, or is it on the...
Both on real devices.
Okay. What's really neat, I like the last bullet point, implement CoAP yourself. It's not that hard. This is one of the most lightweight protocols you could come across. So if you actually look at how the standard is and how it's described, if you actually look inside Contiki and how they implemented CoAP, it's very, very lightweight. It's relatively easy to actually sit down and, on the order of 2 weekends of work, actually implement your own CoAP client, your own CoAP server. So that's sort of a very nice feature of CoAP, is that it's so lightweight, but it's also very simple. Maybe you don't have to make a full featured implementation, just the very bare minimum. Not the block transfer, not the observe, not even the late response. You can build versions of it that are very quick and dirty, and sort of gives you a lot of hands-on experience in implementing an application protocol. So I think I'm going to stop here with respect to the CoAP stuff. There is some additional issues to do with sort of how do I explain what I'm actually asking the server to give me. Now, in our context, how did you know to bring up this slide? You made an HTTP request, but how did you figure out where to make the request to get the information you needed? Like, you all started looking at these slides. How did you know where to find it? I told you, right? I gave you the URL, right? But if these are machines talking to each other, when do they know to give each other the URL? Who told them to ask for that particular information, right? So the problem is that, especially for certain IoT applications, you want to build it in a way that it's all self-running. I don't have to program into my client every possible URL that's out there. And so core, and there's other approaches as well, try to get into that question of how do you discover what that server is capable of giving you. Right? And so if you have a systematic way of explaining, these are the kinds of resources I have access to, then I can tell you about. I have information about this type of sensor, this type of actuator, and so on and so forth. So core, which we're not get into, is sort of addressing some of the semantics of what should I ask for, what can I ask for, how do I ask for it. So some of those issues are covered by things like that.
So are they broadcasting all the time?
No. You would typically have defined some protocol mechanism to go and ask for what do you have, and then they will have a way of describing that information to you.
So it doesn't flood the network with constant broadcasting.
Okay, so we'll stop there with the CoAP stuff. Pradipta, you have the NDAs to send around. Why don't we do that first? At the point when he was giving this tutorial for that company, and definitely manufacturers of embedded processors like ARM are very much interested in the IoT space. So let's dig right into slide 4, which talks about the Web of Things protocol. And just sort of gives you a very quick high-level overview of it. Basically, it's an IETF standard that runs on top of UDP and has requesting the object's URL information, all of that. If you really add up the number of bytes that you need to describe all of this, it's on the order of thousands of bytes. And as we've discussed over and over again, communication energy is a big part of these devices. The reason the radio duty cycling work exists, that we talked about last time, is because keeping the radio on, sending information over the radio is really expensive. So cutting down the amount of information you're sending over the radio is really important in that space. In fact, there was a quote from many years ago that every byte a mode transmits brings it a moment closer to its death. So if it's running much, the person who came up with CoAP, or worked really hard on it, Zach Chilly, and he I've run across work of his over the years in many, many settings, but he's been sort of one of the, I would say, leading industry people behind IoT protocols. And CoAP was sort of one of his pet projects, but before that he'd worked on Zigbee routing. A lot of Zigbee routing was also due to Zach's work, so somebody I have a lot of respect for. You'll notice the slides say ARM. He works, I guess, or did AA batteries. Literally every byte is part of how long that thing's going to last, right? So you really care about optimizing. So really, if you look at the other end of it, at the individual node, they're running 6-LoWPAN, UDP. The CoAP is sitting on top of that, and the web object. All of this somehow they managed to compress down to tens of bytes. In fact, what's really, really neat about CoAP is you're turning these little modes into web servers, effectively. So the fact that it's even possible, I thought was pretty amazing. Support also for apparently SMS, and gives you some security on top of that. The slide 5 kind of points at why you need a new way to think about client-server mechanisms for this new space. So if you look at a typical sort of web application, the amount of information that's embedded in the packets that are going over the network is on the order of thousands of bytes. So you have to have the IP information, the TLS information, the HTTP information, plus whatever your